temporarily conclude our posterior predictive stuff. We'll come back around as we start looking at non-i.i.d. models, so on and so forth. I'll leave you with a couple problems that I'll work out some of the details. Last night we went over how to solve the integral directly for the normal case. So we've been looking at this problem. We've already got a solution for it. I had made a mistake on the board. I forgot to invert my variances when I put back that onto the board. So I had seen that at the very end. So I thought I would just show you the correct math. Very easy to make a mistake as you're doing this. So it's good to know what the answers are in advance. You know, if you're doing a midterm or something like that. This integral that we would solve explicitly, this is what I had asked you to do on the homework. You can go through some of the details if you'd like. I'll just leave it up. We went through this integral last night. And after I got off of Zoom, I was like, let me just finish out the expectation. Oops, I forgot a minus sign. So it was there. But I think this is all right. I think this is what we worked through last night. So we wrote down this integral. Right here, that's the posterior predictive distribution. So I've got the sampling distribution. I'm going to integrate over the posterior. Again, what is forecasting? In the i.i.d. case, it's just learning the parameters. And all the uncertainty in your estimate of the parameters gets propagated into the forecast. So that's what I like about Bayesians, is they average all their error across everything. So they propagate their error. This is a general procedure, just doing these sort of integrals. In a real time series model, something like that, where you're used to thinking about the term forecast, there might be parameters that govern how time changes. And you would estimate those as well, and that would go into propagation into the future. All your error in those, and how they propagate the signal through time. In the i.i.d. case, time isn't a real thing. Nothing changes through time. And so you're just estimating the parameters. So this is the integral that we would do. So I just write down everything. I choose to write everything down up to proportionality, because all I'm going to do is recognize the kernel of everything. And so I expand, as usual, and I factorize out everything that doesn't have to do with my term that I'm integrating over. So I like to factorize that stuff out. I also got rid of this. I factorized out the x bar there in everything, and I got rid of it, and I wrote down proportionality sign. If I don't need it, check it as you go. It only just clutters your math. Again, what we're going to do is recognize kernels. We don't know what the kernels of distributions are. We don't know what distributions they are. Things get a lot harder. That's where we have computational techniques. We'll be learning a lot about those. So I factorize that out. I can already recognize, like I've said a couple times now, this posterior predictive is going to be normal. I've got e to the minus a quadratic term. I happen to know that this will induce only quadratic stuff in x tilde. How do I know? Because I've done the integral. I'll do it for you in a second. But this is a normal with some expectation and some variance. And by knowing that expectation and that variance, I can figure out what this thing integrates to. It's the completion of the square term that you end up looking at, and it gets flipped over. We talked about that in detail last night. But I did write down everything so that you can follow the correct math as well. And so I find my e and b term just by looking at the quadratic and the -2 linear term inside the integrand of this thing right here. So this is a normal with an expectation and a variance. I can recognize which normal it is. And so what I do afterwards, essentially, is I just figure out, I've already got this term right here. That was here. And what we figure out is that our integral integrates to something proportional to this. This is the completion of the square term. E star squared over b. There's a plus sign there because it's getting flipped over. The square root 2 pi, b star, flipped over, I've left that out. It doesn't have any x tildes in it. Doesn't have anything to do with anything. And so this is what that integral integrates to. Again, there's also a square root 2 pi b star. So this whole term right here is that integral. And I can recognize that because I know what normals integrate to if they're normalized correctly. They integrate to 1. So this is all the stuff that's left over from that kernel. And that's what completing the square does for you. It always turns out to be the e to the plus e squared over variance term. So that's what they are right there. And then you just solve everything. So I multiply these two things together. I plug in my e star, and it's a big mess. So you got to just be detailed in doing everything. So I went through the steps, but once I write down what this integral is, the whole thing is that, which simplifies to that. I recognize this is a quadratic in x tilde, as promised. I combine all my quadratic terms. I combine all my -2 linear terms. And then I recognize which normal it is. So I do that same recognize where the quadratic term is and the -2 linear twice in this problem. Once for mu in the posterior that I'm integrating over, and then once for x tilde. So I'm treating the random variables in 2 steps. Okay, so everything simplifies. You wind up with sigma squared 1 plus 1 over n. So that's sigma squared plus sigma squared over n. That's the posterior predictive variance. Sigma squared over n is coming from your posterior estimate of mu, and the sigma squared is the variance of the future sample. So one of the variances is attributed to the parameter, and one of them is attributed to the sampling distribution. So I like that this decomposes so nicely, so we can kind of see what we've been talking about. In other distributions, you don't see this decomposition quite as nicely, but it's there. So the expectation and everything, once you cancel everything, I told everybody last night, it's a big algebraic mess, but it turns out to be x bar. It is x bar. So you can go through that. We had last time done this a little bit simpler. And so both of these tricks are useful. Sometimes you got to do the integral. You don't know what the distribution is. Sometimes if you know the distribution and you know it's parameterized just by an expectation or a variance, like in the normal case, all the other moments are 0. Symmetric distribution, there's no kurtosis and stuff like that in the normal distribution. So once I recognize it's normal, then all I need is the expectation and the variance. In some distributions, that's not going to be enough to define the distribution. So like in a T, we need to know what the degrees of freedom are, things like that. The extra little things that define the distribution. When we use the iterated expectation formula, and again, we're taking the expectation right here over x tilde, given all that stuff, and then this is the expectation right here over x tilde given everything, and this is going to be the expectation over mu. Remember, if you see an expectation, think of it this way. An expectation is a function of the terms you condition on. If it has anything else in there, you've messed up. So, anyway, once you do this, you get mu just back. This is normal. So that's that parameter right there. If this turns out to be the parameter of interest that you're integrating over and not a function of it, this expectation will be the same expectation as the posterior has. And we can see it right there. This is the posterior expectation. So if that's not if that's just mu and not a function of mu, the expectations stay the same in your posterior inference and in your forecasting inference. That's not going to be true if this interior expectation is a function of the parameter that you're integrating over. It's going to be a little bit harder. Well, we did a problem like that. So I designed more complicated problems during my office hours for Mohammed last week. The variance, we go through the iterated variance formula. Very easy formula to remember. Never remember if it's the expectation or the variance of the variance or the variance of the expectation. It's both of those things and add them together. We went through a proof of the iterated expectation formula. Very similar proof for this sort of thing. It's in all your probability books. So look it up, go through it. But essentially, you're just showing that the left-hand side is the left-hand side. And they are the same. So you're marginalizing over something. It doesn't matter what this random variable is in general, but to make it useful for our problem that we're solving, it's so that we can figure out these interior expectations and variances, not something totally arbitrary to us. Conditioning on a random variable that you're integrating over is the way to go in every one of these problems. And so that just turns out to be, again, sigma squared over n plus sigma squared, once you go through all that. You can do it two ways. One way saves a lot of time, but knowing both methods, being able to do the integration might be necessary in some problems. Let's do another example, and then we'll move on to integral after we study a couple more examples. I don't think I'll carry all of these through. I want you to think about it a little bit. There's certainly fair game for midterms. And I have you work out some posterior predictive distribution. It's guaranteed. It's a calculus problem. So that should make you happy because it's not that hard if you know what you're doing. But they're all kind of the same. What would I do if I were trying to design practice problems for myself? I'd run through the whole exponential family. And I would do problems for all of those. Figure out what their conjugates are, work out their posteriors. If they've got two parameters, work them out in every way you can think about it, and work out their posterior predictive distributions. If you do that, you'll never have to do it again. So you'll just know how it's all done. You'll know the answers to all of them. Also, in the book, Peter Hoff's book, I don't reference it too much in this class. He's got a lot of these work through for you. Also, Wikipedia has homework through for you. But let's just think about this problem where we've got a known mu and an unknown variance right here. So let me just ask a question. What do you think the posterior predictive distribution is going to be? What family do you think? I'll be real clear with my notation and tell you what is fixed and everything. So mu is fixed and it's given to you. So what if I integrated out sigma squared or some transformation of sigma squared? If I were going to do the problem, I'd flip sigma squared upside down because I remember everything about gamma distributions and I can remember nothing about inverse gamma distributions. Saying that, if somebody wanted me to work with the inverse gamma distribution, I've got me. I could still remind myself what the expectations are. I could probably figure them out. I'm doing some integration by parts technique, but I'd probably just look up in Wiki what is the expectation of the variance of this thing. After you get through your qualifying exams, you're allowed to do that as well. So, last time you ever have to do an integral from somebody is the day before your qualifying exams. That's almost it. If you teach. So then you have to do it every once in a while. What do you think this is?
A normal maybe?
Yeah, maybe a normal. At least we're in the right ballpark, right? It's like x tilde lives between negative infinity and infinity. So if you said like a gamma or something like that, I would say that's only in the positive range. So that would be wrong. So at least you passed the first test. That it's got the same support as a normal. It's not a normal. It's a t. So anytime you integrate over the variance, if you don't know the variance from your Stallman 1 class, you ran off to a t table. So it's going to be a t. T-disk. Once you do this integral a couple times, you figure out the thing you're going to be integrating over is probably a gamma or an inverse gamma, depending on how you parameterize it, and you know how to do that integral. You go, oh, that beta to the alpha term, beta to the minus alpha, that's always a t. Once you do it once or twice, you start to know that. You feel comfortable with it. So it's a t distribution, and there's 3 parameters in here. I don't have an iterated degrees of freedom formula. So that's probably not the best way to do this problem. Also, t's, if the degree of freedom is small enough, 1 or less, you don't have an expectation. The degree of freedom is 2 or less, and yeah, degrees of freedom can be non-integers, technically speaking, so anything less than 2, no variances. So, in general, those formulas are going to apply to this problem. Now, if degrees of freedom are high, if I cranked up n a little bit, give you a couple data points, you could use those to identify the expectation of the variance. If the degrees of freedom were too small, i.e. I didn't give you any data, you're going to have a problem with everything. So it is a t-distribution. If it were me, I would just go for the full-blown integral. This is not a hard integral. This is actually an easier integral than the other one. And so I know this thing, I don't know that. And so when I have to integrate over mu, I just have to complete the square. But integrating over phi is pretty easy. So I'm going to change the problem and just parameterize it like that in terms of the precision. That's just because I prefer. It's not the right way to do this problem. It's the way that all of my American friends know how to do this problem. So, cultural nuance. So you get somebody from England doing Bayes and somebody from the States doing Bayes, and they get together and they do this problem. There's a mild snag where they have to, well, I like working with inverse chi-squareds. Okay. So, no big deal. And so, if you work with somebody that does it a different way, do it their way. I usually encourage people to do that. If you're allowed to be the boss, do it your way. Okay. So, how will I do this problem? Just using the basic definition. So this is going to be integral fx tilde. This has got a mu and a phi in there. And then I'm going to look for the posterior distribution of phi given all of my data that I got from here and data points. So that all goes in here. x1 to xn. And I've given mu as well. So I got to remember I can keep mu throughout everything. So dt from 0 to infinity, that's where phi lives. It's a positive parameter. And I know what this looks like. This is a normal. So I can write down e to the minus 1/2 x tilde minus mu squared. And I'll put it in terms of phi right here. And I better not write it down like this. I better put in my phi right here. If you're integrating over mu and you forgot to do that, no big deal. If phi was given to you, that's a constant. But it's not a constant in this problem. So I've seen a lot of people make a mistake by forgetting that term, getting off, leaving terms where they say it's part of the normalizing constant. It's a constant with respect to the sampling distribution, but not a constant with respect to the likelihood function, which is how we're treating it. And so that constant's not so constant anymore. I often replace that term with integrating factors, because I hate telling people, well, the normalizing constant is not constant. So it's not a constant when you think about it as the likelihood function. It depends on how you're thinking about that function. So put that thing in there. And then we've just got this. Do we know what this distribution is? Probably work it out real quickly just to spot it. But do you know what? It's obviously a gamma. Let's just build a likelihood function. Phi to the 1/2 right here. I goes from 1 to n, e to the minus phi over 2 xi's minus mu squared. And then I'm going to multiply this by my prior. And that's my prior. So I need to tell you which prior we're going to use on all of this before we come up with this. So I'm going to presuppose our reference prior that we kind of like last time. So I'll use that. If you wanted to use a gamma with some parameters plugged in there, the math is identical. Just have a few extra terms floating around. And so this is just phi to the n over 2 minus 1. I love it. That little thing pops out there. I love that minus 1 term. It always pops up for free. E to the minus phi. And I'll pull everything over just to make it look prettier. So this right here is a gamma with parameters n over 2 and some of the xi's minus mu squared over 2. What's the expectation of this thing? Some of the xi's. We'll just say expectation of phi given everything and mu. This is equal to n over 2 over some of the xi's minus mu squared over 2. Those two's cancel, so it looks like the thing that you would use for the MLE, flipped over. Saying that posterior means and MLEs, they don't have the same properties because one is a distribution and one is not. So very different things. There's a Jacobian term that comes in on distributions when you transform them, but in likelihood functions, it's not there. We'll talk about that later when we talk about maps and finding modes and things like that. So I could probably do this integral right here. So this integral is integral 0 to infinity. I've got my phi 1/2 plugged in right here. I've got my e to the minus phi. This is just going to be x tilde minus mu squared over 2. And then I've got my gamma distribution right here to play around with. So this is just going to be phi to the n over 2 minus 1. And then I've got e to the minus phi, sum of the xi's minus mu squared over 2 d phi. Let's give ourselves a little bit of space here so we can think about it. So that's my integral. Let's write down one more simplification. Right here, combine some terms. This is going to be phi to the n plus 1 over 2. So I've just combined this with that. The n plus 1 is coming in, and guess what that's telling you? So that's that extra variability of that little extra 1 point. So we'll let you think about that a little bit. E to the minus phi. And then I've got a couple terms in here. X tilde minus mu squared over 2 plus sum of the xi's minus mu squared over 2 d phi. And that's an integral I know how to do. This way, should I make my mistake?
Would the first term to be n minus 1 over 2?
How about that?
Oh.
I like it like that. I like that minus 1 always hanging out, but yeah, you're right. So I've taken it so for granted that I don't even write it down anymore, but it's got to be there. So I just combine these, then I know what this is. I know what this thing is. This looks like a gamma. And it's got 2 parameters, n plus 1 over 2. And then I've got this thing right here, x tilde minus mu squared over 2 plus sum of the xi's minus mu squared over 2. Hopefully that's not too messy. It's just that stuff right here that I usually call beta tilde. And this stuff right here I call alpha tilde usually. So I know how to do this integral. It's proportional to beta tilde the minus alpha tilde. If you would like to write down gamma alpha tilde, you're at liberty to, but that's a number. Keep in mind what the alpha has to do with. It has to do with n. And I'm going to presuppose you know what n was in the problem. And so we can get rid of that. This thing right here, if you write it all down, it's going to be x tilde minus mu squared over 2 plus sum of the xi's minus mu squared over 2 raised to the minus n plus 1 over 2. What do you think that distribution is? We already know. That's a t. It's definitely a t. What I would like on all of this is I would like this. That kind of looks like a t. Here's the random variable of interest. X tilde. Oh, I already know where it's shifted. I know where this thing is centered. It's centered at mu. This thing is squared. What do t's look like? Let me remind you. T's look like this. With center mu, scale sigma, degrees of freedom mu. They look like this. proportional to 1 plus whatever my variable is. I'll call it C, since I'm just talking about the variable in general. So a side, usually what I say right here. Z minus mu squared over sigma squared degrees of freedom minus degrees of freedom nu. And then what goes here? I know there's divided by 2 plus 1. Plus the dimensionality of the problem. How that comes in. So how do you do this, class? You know your distributions. You know the kernels of them, and some of them you know their integrating factors. Makes everything super simple. So if you're not carrying along the distributions, remembering them, you're sure making your life harder come midterm time. So what do I do right here? I divide everything by this. Boom. It kind of looks like a scale term. So I divide everything by it, I factorize everything, and then I recognize what the degrees of freedom of the problem are. So the degrees of freedom in this problem is n right here. I need to make sure there's an n down here. I have to factorize it in. You're going to be plugging that n in by introducing it into the scale term. So you're going to multiply it by it, divide by it, and re-recognize what the scale is. The scale is going to look like this thing divided by n. So I'll let you do that math yourself so you can complete it. But basically, I can recognize this. It's centered at mu. It has scale sum of the xi's minus mu squared divided by n, and it has degrees of freedom n. So if you can't see that, figure out how it goes from here to here. Again, you need to divide by this term, factorize it out. Nicely, there's no x tildes in there. Mu is given. That's a constant. I can just kind of play around with. So I'll just write it down. This is the answer for our problem. X tilde given cap x in mu. It's going to be a t centered at mu. It's going to have scale sum of the xi's minus mu squared over n. I suppose this is supposed to be square rooted if we're going to call it a scale. I always go back and forth. I can never get my variances and my scales right. So when I talk to a class, but hopefully you get the point. And degrees of freedom. So that part's already so good for us. I'll let you go through that, tidy it up. That's one of the tricks to a midterm question that comes every single time. You have to recognize your T and get it in the right form. So I'll leave a little bit of work for you. Any questions before we just touch on another example? Cool. Let's try this one. New example. And again, I'm not going to carry it all the way through for you. Leave a little bit. If you'd like to know the secret, I did do this integral, the full-blown thing, in my last year's class that is on YouTube, so you have to find a day. So if you do want to see it all worked out, I did it with Chuck. So it takes a whole lecture to run through all those steps and tell you about things that maybe you've forgotten about. But let's say this is a binomial, and we'll do one data point. I've got plenty of asymptotics because I got an n in there. I'm going to assume my n is bigger than 1. Okay. So what's my prior that I'm going to pick? If we're Bayesian, before we do any of this, we better say which prior we're going to use. What would you use? Beta, yes. Which one would you choose? Yeah, half-half's a good answer. Like that should be your knee-jerk reaction. Half-half. That's right. Later on, we will do a derivation, and I'll show you where the halves come from. But I've been saying for a while, it's a really good choice. So I haven't fully justified that. But if you go through that simulation exercise in homework 2, you'll start going, oh, this is kind of cool. Accumulating these endpoints in just the right way. We'll go through a derivation so that you're wondering, is this just all intuitive? No, there's math behind it. So this, I'm going to pick to be a beta. You could call it whatever you want. I'll call it alpha and beta right here, just to keep it kind of general. But usually I think these would get out. If I didn't know anything about the problem, that's where I would go. We will keep that conversation going. I want to show you things before we get there. So if you're still a little confused about this, that's good. We will clarify that. Okay, so now we're ready to do the problem. We collect a whole bunch of data. If we are doing coin flips, we summarize the number of successes in coin flips, and that's what that means right there. What distribution do you think this is? X tilde given X. There's no choices of anything to lock down. These are only parameter. So nothing's new in this problem. So this is going to be fx tilde given p. It's going to be pi p given cap x. P. Where does p live? 0. Probabilities aren't smaller than 0, and they're not bigger. Why? Because we made that up. So, totally arbitrary. So, but we all are used to it, so we like that. Okay. So, all we have to do is just write down what all this stuff is. So, what is this? This is going to be p to however many successes I have. X tilde 1 minus p to the n minus x tilde. You can write in your n x tilde right here. The normalizer for the common quirks of all the different ways you can shuffle the data. N coin flips and still have x tilde coin flips. So this isn't necessary right here, but if I get rid of that, I'm going to have to write proportionality. Usually in this problem, when I do the integral, I keep everything there. So I kind of think it's useful in this one problem to keep everything in there. Because you might not know what this distribution is. So I like to look at everything. Oh, and if we got rid of that, we would have also got rid of our random variable. So you'd better not get rid of it. I actually said that quite unintentionally. I was thinking for a second, toss that thing, because you're usually tossing it. But this one actually has a random variable in there. You can't get rid of this. So this needs to be here. So probably a good rule of thumb is write everything down. Look at it carefully before you throw it away. And then this thing right here, I think we know what this is right here. This is going to be some beta distribution. So which beta is this? It's alpha plus yeah, it's just going to be the x, right? So this is just x. One data point is my thing. Alpha plus x. Beta plus n minus x. Couldn't be easier. So we can write that thing down as well. So this is going to be a beta. Alpha plus x is a minus 1. It shows up right there. 1 minus p beta plus n minus x right here. And you would have your integrating constant as well. You can keep that one around if you'd like. I would probably say keep it around. So you've got this beta function, which can also be written down in terms of ratios of gamma functions. So gamma alpha plus beta divided by gamma alpha gamma beta. I'll let you write that down. It's helpful in recognizing what this is. I think next week I'll ask you what this whole thing is. Do you have any idea what this distribution is? We could figure out the expectation and the variance. It turns out those do define everything in the problem. How do I know? Because I've worked it both ways. So we could figure out this expectation if you wanted to. So we'll leave this as a question, come back there in a moment, but let's just figure out what the expectation and the variances are. Turns out they both exist in this problem. So expectation of the expectation of x tilde given p and cap x. Given cap x. Right there. This is going to be our expectation x tilde given cap x. What's that? What's this expectation? Comes from the sampling distribution. Keep in mind, if I know p, no data can help you. So that always goes away. In the i.i.d. case, no data helps you if you know the parameter. Give me the parameter, throw your data away. If I trust you. So real statistician, I don't trust anybody. Not anything, I'm going to check myself. So I think that's the attitude. So what's this? NP. So pretty easy. So this is going to be the expectation of NP given x. So you can already see this doesn't have just a posterior expectation to it. It's got an extra n in here. So this is n times the expectation of p given x. What is this thing? I have to look back over here. So this expectation of p given x is going to be alpha plus x over alpha plus x plus beta plus n minus x. This over the sum of those two things. So it's going to be bounded by 1. I can check that, think about the formula in terms of that. That thing always between 0 and 1. And so that's what that expectation is. So this whole thing is n times that. That's kind of cool. So probably what you might guess and try to build yourself. I don't know, maybe I'm just saying that. We could do the same thing for variance. There's no extra tricks there. So let me just ask one more time before I tell you about intervals. What disk do you think that is? What can x tilde be? It's got to live between 0 and n. Or counts. The original x came from a binomial distribution. It lived between 0 and n. If you're going to predict something, it's got to live between 0 and n. So you think it might be a beta binomial, but keep it. Let's talk about intervals. So I'm going to move on, play around with problems, see if you can do them. That's the name of the game. Intervals. So the intervals I want to discuss are confidence intervals versus credible intervals. Now I like wordplay as much as a lot of people. I'm always kind of interested in where the names came from. And I've never really gotten a satisfactory historical answer on who came up with the word credible. I know where the word confidence comes from. If you are reading the book, Lady Tasting Tea, there's a whole chapter on it. So you've got that history book in hand. It's a nice chapter on it. I've got about 3 of them on my desk. Be happy to give them out to you guys if you'd like. We're going to do a little reading group on that. So interesting stuff. What are confidence intervals? Let me just tell you real quick. I assume you know. Am I totally wrong? I assume you had a stat class, and the whole world is talking about confidence intervals all the time, right? Confidence interval. Give me the confidence interval. And we always get like knocked around by our Stat 101 teacher because they say we explain it wrong, but they tell us kids. So maybe I don't know if they say that. So they're intervals that cover the truth. So if I have a problem that looks like this, played around with them on your homework, they're supposed to cover. So we've got a couple different brands. We have exact intervals that do cover at 95%, we say they do. We've got the asymptotic variances that we hope cover. And we saw in our homework that in the binomial problem, we built that asymptotic interval that you use using normal theory. X bar is governed by normal stuff eventually, but if n is small, then over by the endpoints, those intervals didn't cover very well. So nothing annoys me more than people walking around with asymptotic intervals that don't work. And they're like, well, the theory says. Because then it gets big, it's like, you've got 18 data points. So sometimes they'll say, well, I've got 45, and in that problem we were trying to study with a small p, 45 is not going to do it either. So if p was relatively small, if you're under 1%. I tend to think that what we study nowadays is stuff where things are rare. So we've already figured out all the stuff where it's like totally common. So all those intervals, those walled intervals that people used estimating p's that were between like 0.2 and 0.8, that was fine, no big deal. But now that people are studying more rare problems, that same interval is really clumsy for big P or small p. Just is. So you've seen it yourself. So confidence intervals are supposed to cover the truth at some level. So, i.e. usually 95%. That's the standard. Not 95, not 94%. If you go to Nate Silver, do any of you watch and read 538 every once in a while? So he's a journalist, but he does analytics. So he's always trying to, like, here's the numbers, here's my weighted polls, here's my poll numbers. He shows intervals all the time. So I think I look at him for the election every once in a while. About a month ago, I said, I'll start looking at Nate's numbers. I don't want to look before because there's too much that's going to change. So I don't want to get too invested. Last time he had it, Hillary was going to win 60% chance and Trump 40%. That's not a bad prediction. You know, that's pretty close. His intervals were super wide, if you've ever noticed. Super wide. Those surfaces that he was predicting were pretty flat. And so he uses 80% intervals all the time, so he can trim them down. Use 100% interval, covers the whole domain. You're going to cover everything all the time. So 100% interval is not a good interval. So if your parameter lived between negative infinity and infinity, your 100% interval sounds great. The only way I can give you a guarantee is to say the answer is between negative infinity and infinity. So, terrible answer. You want your intervals to be narrower so you can drop the rate if you want. Big Nate uses 80% intervals because that thing is very flat. It's going to be closed, it looks like. So, I think he says 75, 25 right now. Checked a couple days ago, who knows what it is. We'll pay attention in another couple of weeks. Maybe the Friday election, we can look at it and make something about it. Everything changes all the time. Okay, they're supposed to cover. So the idea is that you have some function that computes your interval. So function to compute interval. In the case of normal data, xi is coming from a normal thing, mu sigma squared, right here. You usually end up picking your interval to be x bar minus 1.96 times the standard error. So if you didn't know what sigma was, then you might estimate it. So you might say xi minus x bar squared over n minus 1. And then you need to divide this by n, square root of n, is what? So that it's getting smaller asymptotically. So the thing at the inside estimates sigma. So this is sigma hat. And the other point is going to be x bar plus 1.96, sum of the xi's minus x bar squared over square root of it. You could have put the n inside. This is has an n minus 1 here. Okay. So x bar plus and minus some stuff. The 1.96 comes from the 95%. And this interval right here, if your data was actually normal, this is a 95% interval. And you've learned about this in stat class, or if you've read any research paper anywhere, somebody probably did this. You know, at least if it didn't have a statistician attached to it, probably somebody did something like this. So the idea is this interval. So I'll just say we've got our lower limit and our upper limit. The idea is if I generated n data points from this thing and I develop my interval, so let's just say this is lower and upper, there's a chance that that covers truth data. So the interval is random, theta is fixed in the classicist mindset. And that's okay with me. So there's some theta. This interval, the way that I've drawn it, happens to cover theta. Now if I generated another n data points, I would construct another interval. It would look a little bit different. If I generated n more data points and I did the same thing, I'd get some other interval by chance. I do this over and over again, and some of these intervals would cover the truth, and some of them would not. So that one did not. If this is an actual interval, and it doesn't just supposed to cover, it actually does, and in this case, this one works, that 95% of these intervals will cover the truth. And that's true. Bayesian thinks about their intervals differently. They think about the probability that your parameter lives inside of them. It's a belief statement about everything. Now, if the Bayesian was doing this exact same problem, and they did all of this using reference priors. So if you didn't know mu and sigma squared, you did everything based off of the t-distribution. That's how these intervals are being constructed. You'd come up with the exact same interval if you use reference priors. So the Bayesian's interpretation of this is whether or not the parameter lives inside. And they agree with each other. In the normal case where you know sigma, we agree with each other, we get the same intervals. In the case where we don't know sigma and we use standard reference priors, i.e. mu is proportional to 1 and phi is proportional to 1 over priors on those parameters, respectively. We get the exact same thing. So for this, the Bayesian and the classicists agree we have different interpretations of our intervals. Saying that, there's a lot of examples where we do not agree at all on how to construct the intervals. And so I want you to think about the examples that are coming from this norm, that are induced by normality. If you think about x and mu, they're symmetric in each other. And so if you have that symmetry, and you think about what Bayesian versus the classicist is doing, we're basically moving the arguments, building an interval for x, or we're building an interval for the actual parameter. And so when you have that symmetry, chances are Bayesian and the classicists are going to agree. If you use standard reference priors, they're going to agree with each other. But in problems that don't have that symmetry, there can be a gross disagreement. And that's what I want to come back to next time. So I want to study this problem. I'm just going to write it down real quickly. You're going to get xi, and it's going to come from a Bernoulli distribution. You know what? Since we don't have enough time, we're already over. We'll come back to this example next time. I'll show you an example where the Bayesian and the classicists don't agree on it. And so just to highlight some of the stuff there. So Monday, thanks, guys.